All right, well, good morning and welcome to day 3 of emergency COVID online class. Hopefully everybody's doing well and to survive the week. Today's plan is just to keep showing you more physics examples. We're going to talk about fluid forces, the forces on things that are underwater or submersion fluids. We'll talk about centers of mass, which is basically trying to figure out where we could treat an object as one point and a couple things like that. So that's my plan today. But before I take off, I'm just curious if there are any questions from last time that you guys have or any homework questions you'd like to look at. All right, well, I was about to say I'm not hearing any or seeing any, but Juan just threw one in the chat. You'd like to see number 10 from 2.5. I'll put that down on my list. Any others? Oh, all right, well, then let's go take a look at that. Go ahead and switch my screen here. All right, so hopefully we can all see the homework set from 2.5 and we'll jump down here to number 10. Okay, so this one says we want to find the mass of a two-dimensional object. And it says it's a frisbee of radius 5 with a density function, rho of x equals e to the minus x. Okay, so frisbee, just a disk. So we've got it here, radius 5, and we've got a density of rho of x equals e to the minus x. Now, I'm just going to tell you, me reading this question, I think that they have kind of miswritten this. I think what they mean to say here with that density function is that it's not a rho of x, but it's a rho of r. That's my hunch, because otherwise this is a really, 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 really difficult question. All right, but let's talk about it. We'll kind of talk about it both ways. So you can see what I mean about the how much more difficult it is if we take it as written. But just go here real quick, write that down. All right, so let me go ahead and go to a whiteboard here. See what we can do about this. All right, so again, this is 2.5, number 10. So here's the picture. We've got our frisbee, and we know that it's got a radius of 5. Now, they told us a density function, or they gave us a density function of rho of x equals e to the minus x. Now, this just means that we don't have constant density, that it's getting heavier or lighter per unit, depending upon where we are. Now, let me start with the why I think this is a typo, that they don't really mean it in terms of x. So think about what this is saying. This is saying as we move to the right, our density is going to be affected by this formula, right? So here's my problem with this, and why I think that they didn't mean x. Where is our disk located? Like, what are the x coordinates for this frisbee?
I guess it doesn't say, does it?
Right, it doesn't say. And that's kind of what I'm getting at, because if you're going, oh, I don't know, Yeah, we don't know. I mean, are our axes here? What if our axes are over here? What if our axes are there? Right? Depending upon where our axes are, this is going to give us very different answers. Right? Like think about for the very first ones I drew, our x's are going to be positive, you know, not super huge probably if this is to scale, but they're going to be positives. Think about compare this one. If our axes are over here, our x's are way negative, which is going to make this much bigger. And so we get a completely different mass. So this is what makes me think that they just kind of miswrote this. I think what they really wanted, and we're going to try this and we'll see if we get the right answer this way. Let me change my color back. Or I think what they wanted was actually rho of r equals e to the minus r. Because now think about that. Does it matter where our disk is at this point? No, not at all, right? If all we've got is that, then, well, okay. Our radii, they're going to go from 0 out to 5. Okay, cool. We can do that. That's not a problem. Okay, so you feeling all right with making that assumption? And just to help confirm that's what we want, if we go back and we look at the book, so I've got the book open on another page here. Let me go ahead and share that. So this is in section 2.5 and it's theorem 2.8. Hopefully you guys can all see it here. It says mass density formula of a circular object. Right? And so here it says let rho of x be an integrable function, means you can integrate it, representing the radial density of the disk. So that's why I'm saying it's a density with in terms of radius. So this is one of those situations where you kind of have to be careful. X may not mean exactly what you think it means. And if I was writing this book, I would have used a different letter than X. But I didn't write the book. So it's always good to go back and kind of confirm and make sure everything looks like what we need. All right, well, anyway, so this is a radial density. Excuse me, that formula e to the minus x. All right, so seeing I have this up here right now, let's take a look at that formula. So it says here that the mass is equal to the integral from 0 to r. So that's the radius of the disk. So for us, it's going to be 0 to 5. And then we've got 2 pi x times rho of x dx. Now, I didn't show you one of these, but let's just talk about this real quick and see why this is giving us what we've got. So let's think about what does 2 pi x or 2 pi r give you? What does that make you think when you see that formula 2 pi r?
The circumference of a circle.
Okay, so that's the circumference of a circle. So at any given x, any distance away, right, that's going to be that circle. So that's that circumference. We're multiplying by a little dx, which is giving us thickness. So this 2 pi x dx, that's the little ring. And then we're multiplying that ring by the density. Okay, so area times density gives us mass. So all that is in the integral, the 2 pi x rho of x dx, that's the mass of a ring. And then what we're going to do is we're going to take all those concentric rings, add their masses, and it's going to give us the entire disk. So if you kind of break it down, you can see why that formula is going to give us what we want, which in this case is going to be the mass of that object. Okay, so let's go back to the whiteboard and let's actually calculate the sucker or get it set up. All right, so if we use their formula, the way that they've got it written, so we'll leave it as the rho of x, but basically all this is saying is that, like, that's our x-axis basically, it's just radial. Our mass is going to be the integral from 0 to 5, because we've got a radius 5 disk. We're going to have 2 pi x, right? So 2 pi r times the density, times e to the minus x dx. So that's what this should look like. And I'm going to go ahead and real quick go back to the book, and then we'll come right on back again. So if we go back to the book, right? Integral from 0 to 5, 2 pi x times rho of x dx. So that's exactly what we've got in our whiteboard, right? 2 pi x times rho of x dx. All right, so at this point, questions? We okay with how this thing is set up? All right, so now comes the time to integrate this thing. And unfortunately, this is another one that we don't have a method for yet. Keyword yet. We're going to develop a method called integration by parts that will take care of this thing. But as for right now, this would be all right, let's go and punch this into Symbol Lab. Let's use a calculator, something like that, so we can get our integral. I know a lot of you don't like that, having to necessarily rely on the technology. But we're not quite ready for this yet. Anyway, so what does this actually equal? I don't know. It's whatever it is. All right, so I think that was Juan who asked that. Is that better for that one? Kind of see how to go about that.
Yeah, I was wondering though, how far ahead do we learn integration by parts? Should we start to practice some of these, you think?
No, don't start practicing them yet. But in terms of where they're or when they're going to show up, real soon. So once we get out of chapter 2, integration, that's when we start learning more techniques, and integration by parts is the first one that we learn. So it's coming quite soon. But I wouldn't worry about practicing it just yet. But I actually kind of like the fact that we're running into all these integrals from all these applications that we don't know how to do. And I know you might be thinking, well, that's crazy. Why do you like that? Because it really, the reason I like that is because it's really pushing the fact that even these real simple basic applications are requiring more techniques. And so it kind of shows you how there has to be more. There have to be more ways of tackling integrals, because if we don't develop new rules or new techniques, we're kind of hamstrung, right? We're handcuffed, and we can't do what calculus was intended to do. And if you think about this from a sort of historical perspective, this is why things like integration by parts got figured out, because people ran into these kinds of things going, well, we need to be able to integrate x e to the minus x, but I don't know. And it drove mathematicians to these new techniques, right? So we're kind of doing this the way history did calculus, right? Other than the fact that I didn't front load you with a bunch of physical problems that we couldn't solve. That's the difference with history versus just our class, because the development of calculus started with, oh, we've got all this physics stuff going on and we have no idea how to actually do it. That pushed the calculus, and then next thing you know, boom, boom, boom. Anyway, I feel like I'm starting to preach. So looks like we're good for number 10 there. Any other questions? All right, well, not hearing any or seeing any, I'm going to go ahead and hop up to the whiteboard, and we're going to continue down this path of looking at physics examples. All right, so I will be right back.
I actually do have have one question about the one we just did.
Yeah, go ahead.
So this is the final equation we got, the 2 pi x times e to the negative x. That's area times just rho of x.
So, okay, so it's area times density. And density times area is going to give us our mass in this case. So
Okay.
we always get our mass by multiplying our density by whatever unit of measurement that density is, because like there's a density that's mass per volume. So we
Right.
multiply by volume, or there's mass per area, we multiply by area, mass per length, multiply by length. In this case of that radial density, it's a mass per area.
Okay.
So we're multiplying by the area of the ring, which is that 2 pi x dx.
Okay, thank you.
Yeah, you're welcome. I felt really bad. My poor dog had kind of curled up by my feet, and when I had to get out, I had to push her out of the way, and she's all cranky about that. Anyway, all right, so let's talk some more examples of where we use physics or calculus with some physical examples. And so last time we just talked about plain old mass. Take a density times whatever area, length, and add it up. So we talked about that. And we talked about work, which was force times displacement. And we saw that if we could break things down into the little chunks of displacement, or if the force was irregular, like the springs, we could calculate them. So those are some of the big ones. The next one I want to show you is fluid force. All right. Getting blinded by the sun. All right, so fluid force. Now, I don't know if you know this, but fluids, that doesn't mean liquid. I know that this is a real common misconception in terms of physics language versus real world language. When we talk about fluids in the real world, we usually think about liquids, right? When you're sick, make sure you get plenty of fluids. They're telling you to drink a lot, right? So we think liquids. But fluids in physics are just any kind of matter that can flow and fill a container that takes on the shape of the container. And while all liquids are fluids, there are other things that are also fluids. Gases are also fluids. So like the air that you're in, that's actually a fluid. Anyway, so when we talk about fluids, I want you to remember it's not just liquids. Not just liquids, but liquids are one of them. All right, now fluids all exert force. And there's pressure involved with all fluids, whether it's air or water or anything like that. And I want you to think about this. Think about sometime when you've gone swimming and you've
Sorry, I don't know if this is true for anyone else, but I can't see your camera.
I can see you just fine, so I don't know.
Okay, I'll try leaving and rejoining, I guess.
All right. Thank you for letting me know that there was an issue, but yeah, it sounds like it may be just on your end there, Douglas. All right, so think about when you've gone swimming and you decided to go dive under the water. What do you feel? What do you feel when you go underwater?
The pressure?
Okay, you feel pressure. I was hoping someone was going to say you feel like your head's getting crushed, right? That's what I feel. I feel like my head is getting pushed in on itself. But that is the pressure, and I think that was Tiana who said that. But we feel that increased pressure as we go deeper and deeper and deeper. So it turns out that with fluids, there is pressure involved, and that pressure increases as you go to a greater and greater depth. Right? It also depends on what kind of fluid you're in. Think about this. I just told you that air is a fluid. How deep is the air above us? I know that's kind of a weird thing to think, but like how far up does the air go? How far under the surface of the atmosphere are we actually located? And it's a long way, right? It's miles and miles and miles. Well, it doesn't feel like our head's getting crushed like it would if we were under miles and miles of water, right? So obviously it depends on the fluid as well. So it turns out that if we're going to talk about how much force or how much pressure we're feeling due to a fluid, it depends on a couple of things. So I'm going to put here that the fluid pressure, it depends on two things. One, what kind of fluid? And two is how deep we are. All right, so in terms of a formula for this, what we find is that the pressure, it's actually equal to the weight, not the mass, but the weight, how heavy it is. And it's weight times depth. Okay, so if you know what the weight of the fluid is, and this is actually a weight per, in this case, area. Let me go and just kind of write that.
Is this still part of the physical applications?
Yes, this is still physical applications. Does it sound like physics or does it sound like math?
Physics.
Okay, so it's a physical application. No, that's all good. All right, so weight is pressure. It's going to be a weight per area times depth. All right, so if we want to relate this back to density, because density is usually a little bit more known than the weight, we can also think of this then as density times gravity times depth, because your weight is going to be the density times gravity. I think I mentioned that before, that weight is a mass for, it's a gravitational attraction of your mass, so it's not mass, but it's weight. So as a formula, if we think about what we've been using for these, we get that the pressure is equal to rho times G times H. So that's just the easy way to remember. It's rho GH. So density times gravity times the depth. Okay, so now remember I was talking about we've got miles of air above us and we aren't feeling really great pressure. Well, that's because even though H is big, the density is small. The density of air is just a little bit more than 1 kilogram per cubic meter. So think about that. If you have a meter long box, so a meter is like that far, and I make a box a meter by a meter by a meter, that air weighs 1 kilogram, which is not much, 2.2 pounds. Water is 1,000 kilograms per cubic meter, so it's 1,000 times as dense. So you take that same 1 meter by 1 meter by 1 meter and you fill it with just fresh water, that's 1,000 kilograms. So it's a little bit different, right? Well, I have an example of something that I want to show you real quick that I think is kind of interesting. I told you that back in the day I studied marine science, and one of the things we did was we would send down bottles, containers that would end up collecting water at great depth, and we would send these things down thousands and thousands of meters. Right, so we're out in the middle of the Atlantic Ocean, and it was not unusual to send things down like 3,000, 4,000 meters. I mean, it's deep. It's not as deep as like the Pacific, but it's still pretty deep. So one time, what we did was we just attached to the very bottom of this, like we always had this real heavy weight that would, drag it down. But we attached down to the bottom of this pantyhose that were filled with styrofoam cups. Right, so just regular old like styrofoam coffee cups. And we sent these down, like, I think this one was like 3,000 meters. All right, so we sent them down and then they came back up. And I just want to show you what the pressure of 3,000 meters of salt water does. So here's your good old regular coffee cup. And here's what it looked like when it came out. Okay, so I'm going to go ahead and kind of bring this up closer to the camera. I, of course, decorated it before it went down. You can't really see it because it's kind of faint, but that's our sailing vessel that's being attacked by a giant squid, right, with an island with a sunrise and all that. Okay, but this was that. So all that pressure just caused all of the air that's inside the styrofoam. That's why it's actually good for coffee. It's a great insulator because of all the air. But it shrinks it down to just this thimble-sized thing. So no doubt, pressure is a deal. Like it's a huge deal. And think about that. Salt water is like 1,030 kilograms per cubic meter. You multiply that by a couple thousand meters. That was huge, huge pressure, right? So here's your pressure. Now, I'm talking about fluid force. Force is actually pressure times area. So if we wanted to actually know how much force was acting on that, we would need to know not just what pressure there was, but how much area it had. In the case of the coffee cup, it's what's the surface area, right? How much area do we have all the way around? Because all of that force is pushing, or all that pressure is pushing on all the different pieces. And so the total force acting would be the total pressure applied everywhere. For that styrofoam cup, it was a boat lid. Get it? Boat lid. Oceanography. Yeah, there you go. There's your dad joke of the day. All right, so we're going to take our pressure times our area, and that's actually going to give us our force. All right, so now what the hell does it have to do with calculus? Well, I want you to think about an object that's been submerged in a fluid, and we're going to go ahead and just say, let's say we send something down into the ocean, and we'll actually send down this coffee cup. But let's just look at it from the side. All right, so the coffee cup from the side, I'm going to exaggerate it here just a little bit, but it kind of looks like that, right? Now, each of the pieces of the coffee cup are at different depths. I know it doesn't seem like it matters much, and it probably doesn't if we're just talking about a coffee cup whose entire length here is just a couple of centimeters. But you can imagine if it's something large like a submarine or a dam or something like that, we might have some fairly significant difference in depth. Well, that means that, say, this little piece right here, that I'm going to mark in red, that little strip is actually feeling a different pressure than, say, this strip up in black. Right, the one that's in red, this actually has greater pressure. Remember, pressure was weight times depth. we can assume that the weight of the water above them is the same. That's the same kind of density, which actually, if we're talking about that coffee cup that went 3,000 meters, is not a good assumption. There's some huge density differences as you go deep, as you go through a water column, but that's for another day. So that's got greater pressure, which means we have to kind of figure out what the force is for this red strip separate from the force on the black strip. But if I calculated the force on the red strip, and then I calculated the force on the black strip, and then I did this for all the other strips, and then I added them all together, and then, hey, maybe we're going to make those strips really, really thin. What's that sounding like? At this point, you got it, right? That's going to be another integral because we're adding up a bunch of little things. All right, so here's what we really want to do. If we want to get the total force, we have to integrate. And I'm just going to go here from A to B. Those are going to be our different depths. So, right, we've got the top of this cup, we've got the bottom of this cup. Those are going to be our A and our B. But we want to integrate pressure times area. Okay, so the pressure we just saw was rho GH times the area. Well, in the case of this strip, let's look at, say, this red strip. What shape does that kind of look like? Or if it gets really, really thin, what kind of shape can we approximate it with?
A shell.
Okay, well, let's just think about one dimensional. We're not rotating it. Okay, but yeah, if it was rotational, it would be a shell. I'm sorry, Tiana, can you say that again?
Is it a circle?
All right, it'd be a circle if it was a cup, but we're just looking across. Maybe I shouldn't just go with cup. What if what we were dropping down was something like this? So it's just a plate. So just think, what shape are we seeing? Literally, what shape are you seeing drawn there?
A rectangle.
Yeah, there we go. Don't overthink it. It's just a rectangle, right? So if I want its area is going to be length times width, right? Well, in terms of its width, that's going to be the little differential piece, right? This right here is going to be a dx or a dy or whatever we want to call it, a dh. So in that area is going to be the dx. And so then the other piece we're going to need is actually the length. So here's what's actually going to happen when we integrate these. We're going to have our density. We're going to multiply that to gravity. We're going to multiply that to the depth, to which then we're going to multiply that to the length times our dx. And when I wrote L here, I'm talking about that length right there. So obviously the total force we're going to feel depends upon the shape of this object, because that's going to determine how the L is represented. It's going to depend how deep that object is, or how far down it is, and so that's where the H comes in. The gravity is just gravity. For us, it's always going to be the 9.8 meters per second squared. But then it also depends on the density of the fluid above us. But this, if we can set this up, is going to allow us to calculate the total force that's acting on something that's submerged. Okay, so this is what we're going to use. What we're always going to use. But let's apply it to a situation. All right, so let's try this one. I want to make one that's not terribly easy, like just a rectangle. I want to have some variable width, but I don't want to make it too insane because these can get really complicated. So here's what we're going to do. Let's say that we've got a parallelogram that's submerged in water. And what I'm going to tell you is that the top of this is 4 meters below the surface of the water. Okay, so the very top of that is 4 meters below the water. And then in terms of the size of this thing, let's say that this is 5 meters tall. And in terms of the distances across, let's say that the bottom is 6 meters across and the top is 8 meters across. So what this could be, for example, would be some sort of a dam or a piece of a dam, like maybe there's a, sometimes dams have like water gates that they can raise and lower to allow water through. That's actually how dams are effective at creating energy, right? So maybe that's just something that's submerged under the lake, and here's our object. So here's what I want to figure out, is what is the total force acting on this thing? Okay. So that's our question, is how much force is pushing on this dam? Okay, so we're going to need to use this integral. So let's just think about what we need to be told. First of all, we need density. We need the density of the fluid. And I'll just tell you that this is fresh water. And so we're going to have density of 1,000 kilograms per cubic meter. And at these kind of depths, if we've only got like 9 meters, the density probably is pretty constant. All right, just to let you know, in case you don't know gravity off the top of your head in metric, gravitational acceleration is 9.8 meters per second squared. All right, so we got these. Those are our rho and our g. And then the h and l, those are going to come from our shape. So what we're going to need to do is just figure out a way to describe one of these layers, what the depth is and what the width is. Because then we'll just multiply by our little thickness. All right, so we need a coordinate system. We need to choose where 0 is and then build our coordinates. So I'm going to do something that probably feels wrong to you. Right? I'm going to put 0 at the very surface of the water. Okay, so I'm going to make this x equals 0. But what I'm going to do is I'm going to actually make it so that x gets bigger as I go down. Ugh, what? All right, so that probably feels wrong, right? Because we always make things positive going up. Well, I'm going to make my positive going down. And I'll just tell you that the reason behind this, and there's definitely a reason I do this, you'll see. It makes a lot of sense when we're dealing with fluids. So anytime I do fluids, I always go down. All right, so let's just start thinking about all of this stuff. And we can even start with the bounds for our plate. So what are the x values going to be for our plate? If I start here at 0 and I start coming down in a positive direction, what's the first x we run into for our dam here?
4.
Yeah, that's going to be 4, because we dropped 4 meters before we hit it. And then we keep dropping, and then how far down are we when we hit the bottom?
9.
9. All right, so if we're going to start setting this thing up, our force is going to equal the integral from 4 to 9. So here's the first reason that I do 0 at the top and greater as I go down, is it makes it so that my bounds are always positive. I'd much rather have positive numbers to plug in than negatives. All right, so we're going to go from 4 to 9. Now, I can put in my density and I can put in my gravity. So I'm going to get my 1,000 times 9.8. Okay, so now what I need is to think about one little strip across this dam, about this submerged plate. So here's my generic representative. So the first thing I need to know is how deep it is. How far under the water is that? Well, it depends, right? It depends which of the strips we're in. But I'm just going to say that that is X meters down. Okay, this is the real reason that I go with the top of the water being 0 and positive going down, is so that my depth is always X. It's really easy. If instead you were to, like a lot of people want to put 0 at the bottom and then go up, that's totally fine, but then your depth ends up being like one of the something minus X and all that. No, this is easy, it's just X, plain old X. Okay, so there's our rho RG, our depth. But now we need to figure out how far across is this thing when we're at a given depth X. And this is where the work's going to come in. This is where we're going to have to do something, because up to this point it's been pretty straightforward. Now we have to take into account the shape. All right, so think about what we know. At a depth of 4 meters, our width is 8 meters across. And at a depth of 9 meters, our width is 6 meters across. I need to know at a depth of X meters, how far across are we? Well, here's what we're going to do. We're basically just going to make a linear function. Think about it this way. All right. When here we're going to have X and we're going to have L. So we're going to have our width and we're going to have our depth. So at a depth of 4, we had a width of 8. At a depth of 9, we had a width of 6. And notice that the sides are linear. They change, like their lines. It's not a curve or anything like that. That means we just need a linear function that fits these. In essence, I just gave you 2 points. Find the equation of that line. I know I called it L instead of Y, but we can still find the equation for that the same way. So start by getting a slope. Right? The slope is the change in Y over the change in X. So 8 minus 6 over 4 minus 9, which is minus 2/5. So that's our slope. And then I can use the point slope form. So pick my favorite point. I'll pick the first one. I'm going to get L minus 8 equals minus 2/5 times X minus 4. So L minus 8 equals minus 2/5 X plus 8/5. And so I get L equals minus 2/5 X plus 48/5. So there's the length across given any depth. Okay. You give me any depth, you could say, all right, how far across is this going to be when we've gotten 7 meters down? All right, well, I plug in 7, do the calculation, and I get 34/5. So it's going to be 34/5 of a meter across. All right, so this is going to be the hardest part for sure, is finding how to represent the length. And it can get challenging. Like if it's circular, you can imagine if this was a circular thing, like a porthole on a submarine or something like that, then we're going to have to figure out the width across, having to use some trig and stuff like that. But this one was just a linear function. So that's going to go in for our L. So I've conveniently run out of space there. Let me write this again. So f equals integral from 4 to 9. We've got 1,000 times 9.8 times x times minus 2/5 x plus 48/5 dx.
Hey, Bruce,
Hey, what?
isn't the slope 2 out of 5?
You mean instead of -2?
Yeah.
No, it's definitely negative because as we go deeper, it gets shorter across.
Okay, I was just looking at the -2 over -5.
Yeah, it's a +2 over -5. I just threw that minus
Okay, I see.
on top. No, it definitely should be negative because it's decreasing width as we go further down. But thank you for making sure I'm keeping me honest, Edward. I appreciate that. All right, so just real quick, I want you to see that this is going to be an easy integral to do. The 9.8 and the 1,000, we can bring that out front. So we're going to have 9,800 times integral from 4 to 9 of minus 2/5 x squared plus 48/5 x. If I just distribute. And this is just going to be power rule. It's actually really simple to do. So in this case, with this specific shape, we got an integral that we definitely know how to do and can calculate. But again, I'm going to stop at this point because you know what to do. You know where to go from here. It's just a matter of integrating, anti-differentiating, and plugging in values. Okay, so fluid force, this is another place where we use integrals because we're literally adding up the force on every little horizontal strip. All right, so the key to all of this is when you add things, if you keep adding up lots of little things, that gets you an integral. Every application we've seen, everyone so far that led to integrals was because we were adding up an infinite number of little tiny. All right, so questions on this guy? What parts of this? How about I'm going to ask you a question? Oh, go ahead, Tiana. You were about to ask something.
Yeah, I was just wondering, so if your trapezoid had different lengths on the sides, like if it wasn't symmetrical, if you folded it in half,
Okay,
would you go about finding the length differently?
Okay, so that's a good question. The symmetry of this shape actually didn't matter. If we had had, let's say it had looked like this, so it's still a trapezoid, and let's say we're still going from 6 meters to 8 meters with the same depth. As long as this side is linear, which I was trying to draw a line, but segment, but it kind of got curved on me, so that's maybe a little bit better. In this case, we would still have that same length. It's still going to be minus 2/5 x plus 48/5, because the change is due to a linear change on this side. So having two lines on one side versus two same kind of lines versus two different lines, that didn't matter. Where it would have mattered, though, would have been if it had been curved. So, like, for example, if it had been this shape, like let's just say it was a semicircle, then for sure we wouldn't have the linear progression. And what we would have to do if we were going to try to find the length of some strip right here is use a little bit of trig and geometry. And you'd have to kind of do this where you go, okay, so I've got a triangle, both those sides are length r, because that's the radius of my circle. And then I'm going to have my depth, let's just call this x. You'd have to do some right triangle stuff. and all that. So different shapes will mean finding that length in different ways. We were able to do this just because they had linear sides. But the fact that it was symmetric versus not doesn't actually matter. So that was a really good question. Other questions on this one? All right, so let me propose the question I was going to ask. What part of this is going to cause you troubles when you're doing the homework? Can you anticipate what steps along the way are going to give you trouble?
Maybe like setting it up and where you know how you started at 0 and went down. I could see myself getting confused there.
Okay. Yeah, and that is one that often leads to issues because people, like I said, we're not used to down being positive, right? So I can definitely see how that might be a problem for you. Let me just give you this recommendation. Just always go with surface of the water, 0, positive down. So we're actually think of it more as the axis is telling you depth. We're going in the direction of greater depth. Oh, okay, down is greater depth. But yeah, that is one place people run into problems. Anybody else see another part of this that might be difficult?
I think the integrals might get hard.
Okay, yep, for sure. This could get gnarly depending upon how the length is. Right, the depth. If you always go with surface level 0 and dropping down, the depth is always going to be an x. So it's going to be x times whatever that length is. But I think you're right, Edward, that depending upon what that length is, what this piece is, might give you an integral that's a little bit more difficult. Like this one was easy, just power rule. But as we saw with some of the other ones, when we're multiplying, like if you got an x times some sort of a square root, or even x times e, you know, then I guess be a problem.
Also
Yeah.
finding the length if like the shapes are really weird.
Yeah, and I'll just tell you in my experience, after decades of teaching this stuff, that's frightening to say, by the way. I've been doing this for decades. But with all the students that I've seen over all these years, I see that they struggle the most with finding the length. Because for a lot of us, the geometry isn't a strong suit, you know, it's not one of our strengths. And this is algebraic geometry, right? We're not just drawing pretty pictures. We're having to use algebra to calculate things. So be prepared for that to be the hard part. Because the rho, the g, the depth, the rho and the g are easy, easy, easy. And I'll just tell you that some of these problems are probably going to give it to you in our system. And I want to say, I'm going out on a limb here, but I want to say that the weight density of fresh water is 64 pounds per cubic foot, I think. But the book will always tell you, right? These problems, or if the problem itself doesn't tell you, you can find it in the book for what it is when it's non-metric. But anyway, that's all going to be given to you. So this whole density times gravity times depth, or weight times depth, that's going to be fast. That's going to be really fast. It is going to be finding that length across, especially when the shapes get a little bit more complicated. All right. Well, anyway, so here's another example. Fluid forces, right? Another application. All right, so the next application I want to go on to is actually in the next section. So now if you're kind of playing along with sections in the book, this next section kind of gets its own. It's called, I think, centers of mass, moments and centers of mass, or something like that. But to me, this is another physics example because when we talk about centers of mass and we talk about moments, it's all about its use in physics. But let me show you what this is. And I'll give you the real quick intro to them. And then we'll talk about how we apply this to calculus. All right, so we're going to look here at moments and centers of mass. All right, so before we even get to center of mass or anything like that, I just want to talk about being a kid and playing on a teeter-totter, seesaw, whatever you want to call it. So you guys remember these, hopefully, although you don't see them all that much anymore because I think too many injuries. But teeter-totter, this is the good old, we've got basically just a big board. There's some sort of balancing point, and the kids sit on either side, and they go up and down, right? So y'all know what I'm talking about. All right, now teeter-totters are kind of fun, and I remember when I was a kid, we would always try to get it so it got balanced, so that you would have people on either side, but it was balanced. And that was actually kind of challenging to do when you had people of different sizes, right? Big kids versus small kids. If the two kids weighed the exact same amount, that was pretty easy. You just sit them both out on the edge and you call it good. But if you had kids that were different sizes, you couldn't have them both at the end. If they're both at the end, the side with the heavier kid would sink down. All right, so I don't know if anybody, like if this is even resonating with any of you guys, if you did this as a kid, it might just be my nerdiness made me want to try to balance them with weird combinations of people. But what you have to do if you want to balance it is the heavier person would have to be brought closer to the center, right? So if they were exactly equal size, if they were equal mass, all we need are these two distances to be the same. But if one of them was larger, so let me draw another one here, and we're going to have a bigger kid, and all his weight is in his head. If we have a bigger kid, that larger one would have to be closer to the center than the smaller one. So now the two distances here are not equal. Right? So the distance from the center changes. So this is just what you have to do to balance. You want to balance. Now, in the context of physics, what we're doing is we're equating torques. I don't know if you've learned about torque, but torque is just the ability to, for something, it's what you put on something to make it rotate. But you need the torques to be equal from these two kids. But if we want to break it down into the language of what we're going to be talking about, we just made it so that their moments are the same. Okay, and so the moment, when we talk about a moment, it's going to be your mass times your distance to the rotation point. So you might have also heard the term fulcrum. If you've ever heard the term fulcrum, that's what we're talking about here. But this is the rotation point or the balance point. So in the context of a teeter-totter or seesaw, they're the same thing. This is where it would be balanced, but it's also what we rotate around, right? You can think that board rotates. But it's always your mass times your distance to the rotation point. Okay, so if we wanted to balance some specific objects, all we would have to do is take their mass times their distance and make sure that those are equal. So here's a real simple example with just two easy masses. So let's say that this is our balance beam. And we've got our point of rotation. I'll make it with a little X right there. But let's say I have a 2 kilogram mass. That's 3 meters from the rotation point. Its moment is going to equal 2 times 3 or 6. All right, so I'm going to put another mass on the other side. But on the other side, this mass is only going to be 1.5 meters. Or meters, kilograms. So here's my question. Where do I put it? If I want it to balance, where do I have to put this? All right, well, if we want to calculate that, what we're going to do is we're going to think about a generic distance, call it x, but I need the mass times that distance to be the same as the moment on the other side. So I'm going to get 1.5x is going to have to equal 6. So x is going to be 6 divided by 1.5, which is 4. So I'm actually going to have to put that 1.5 kilogram weight further away from that balance point than the 2 kilogram mass was. So just remember, greater mass means closer to the rotation point. You're going to balance it out. All right, so that's all we mean when we talk about a moment. Now, the other concept here, the center of mass, is basically this. Suppose that I've got some funky shape. Let's see what I've got here that's kind of funky that I can actually do this with. Well, I've got a whole bunch of books, and books are kind of lame. But think about this. I've got a book, and what I want to do is I want to put my hand here somewhere. I'm just going to use like these 3 fingers really close together. But I want to find a point here where I can balance the book on my fingers. Now, if I come over here like to the side and I let go with the support hand, you know what's going to happen, right? I'm not going to balance this. It's going to tilt and fall. All right, well, if I want to actually balance it, where do I have to bring my fingers?
Towards the center.
Kind of near the center, right? So I'm kind of near the center. I balance it. Oh, I'm close. There we go. I got it. Now I'm going to just kind of pivot this so you can see. And you look at where my fingers are. They're definitely kind of near the middle of the book, the center of the book. Okay, well, what I just found there, where I put my finger so that it balanced, is the center of mass. Go figure the name, right? It's the center of the mass. Like, if we think about the mass distribution, that's where this thing is centered. So something like this, it's a book. You notice it's pretty much right in the center of the rectangle. But if I have a different shape, this is a little bit floppy, but maybe we can kind of, all right, so here's a glove, right? So go CSU, Colorado State University, one of my alma maters. All right, so I want to find the center of mass of this. It may not actually be dead center, right? It may not be right in the middle of the ram head because I've got weird distribution of my mass. But the question is, where is it? Now, in physics, the reason that we care about that and that we do that is that then we can take this really big extended object and treat it as if it's just one point. And that's way easier to do. All right, so that's the rationale. Well, center of mass has everything to do with moments. So imagine that we got some funky shape here. And I want to find its center of mass. So what we can do is we can think about this as, imagine that I were to put an axis of rotation. Okay, and I'm going to just start thinking about it like this. So let's say that this is our axis that we're spinning around. Now, if I was trying to balance about this axis, if all my mass is over here, what's going to happen? It's going to rotate into the board, right? So this clearly won't work as my balancing axis. Where that balancing axis is going to be somewhere in this shape. I don't know, maybe it's like this is a mostly symmetric shape in that direction. So I'm going to go with that. Maybe that's the center of mass. So that if this is what I was rotating about, I've got the same mass distribution on each side and it kind of balances. Well, I would want to do something similar with a horizontal axis. And that horizontal axis, I don't know, let's just say that it's like this. So this would be the one at which this thing wouldn't rotate left and right. And where these meet would be my center of mass. Okay, so what I'm really trying to do is balance around two teeter-totters. I've got a teeter-totter that's going left and right horizontally, and I've got one that's going up and down vertically. And I'm trying to balance about both of them. Well, if we just come back to one of these axes, so let me erase this one for a second. The way we're going to actually find that axis is by looking at the moments of all the little pieces. So like think about this little chunk right there. It's got a certain mass, and it's got a certain distance away. So I can calculate its moment by taking its mass times its distance to that axis. And then I'm going to do that for every little chunk that makes up this object. Right? So I'm going to be able to calculate the moment of that little guy, and the moment of this one, and so on and so forth. And what I'm going to want is that the moments on one side are going to need to counter the moments of the other so that we can balance it. All right, well, why is there calculus here? I'm breaking this object into a bunch of little pieces. I'm calculating the moments of each of those little pieces, and then I'm adding all those moments together. I'm adding up an infinite number of teeny, teeny, tiny things. Integral, just like every other time. So that's where calculus comes in here now, is that the process of adding up all of these moments. Okay, so how are we going to actually do this? Well, we're going to look for centers of mass of two-dimensional objects. And here's how we actually calculate these things. If you want to find the center of mass, first of all, the symbols that we use for center of mass are X bar and Y bar. That's what we say. We say X bar and Y bar. So it just has a little bar across the top. If you've taken statistics, you may recognize that as mean. We do the same thing when we talk about means or averages. And so basically, this is just saying this is the average X. And this is the average Y. All right, so we're going to label them X bar and Y bar. And how we get those, like X bar, this is going to equal the moment about the y-axis divided by the mass. All right, so what do I mean by moment about the y-axis? Okay, well, here's my y-axis, let's say. And I'm looking for the rotationalness about the y-axis. So it's all going to be about the mass of the little chunk times its distance from the y-axis. So that's what I mean by moment about the y-axis. When you look at this in the book, I really don't like this notation, but I write it this way. Don't write it as big M sub y divided by little m. So that's your moment is the capital M about the y-axis divided by mass here. So then similarly, y bar, that's going to be your moment about the x-axis divided by the mass. So there are three things that we're going to have to calculate when we do one of these. We're going to have to calculate the mass. We're going to have to calculate the two moments. All right, so let's just start taking care of these three things. Now, the mass is actually pretty easy. For all of these, we're going to be given a density. But this density is going to be a mass per area. Okay, so for every one of these, when you get a density function, it's going to be a mass per area. And so if we have a density that's a mass per area, what do you have to do to get a total mass?
Multiply by the area.
I'm sorry, say that again.
Do you have to multiply by the area?
Yeah, it's just times area. Okay, so we need to get, if we're given a density, then the mass is going to equal that density times area. Now, let's think about this in the two different ways that could happen. One is we could have density that's constant. If we've got constant density, then that's awesome. We just take the area of the shape and we multiply it by that density and we're done. But if we have variable density, if it's a density that depends on x, then we're going to have to use an integral to get the total mass. So let's look at a shape that looks like this. So we're going to have our f of x on top, our g of x on the bottom. And so let's say we've got a density. For these problems, for the ones you're going to see, because we're not ready to get too complicated yet, so you'll get there. For these, we're going to have densities that are functions of x. Okay, so our density is just going to depend on where we are in the x direction. And so if I want to get my mass, I want to cut this into strips that are at the same x, because then they've got the same density. And I would have to multiply that density times the area of that little rectangle. Well, area of the rectangle should make you think area of the curves and all that kind of stuff. And so what we're going to get our mass is, it's going to be an integral from a to b of the mass of the density, so rho of x, times the area of that strip. And the area of that strip is going to be f of x minus g of x times dx. So remember when we did area between curves, it was exactly this integral, but without the rho. Well, now we just need to have that rho in there because it's density times area. All right, so that's how we're going to get our mass. Super easy, super easy. And we're going to love it when that density is constant. Because if that density is constant, we just pull that out, and it's basically find the area between those curves and then multiply. All right, so that's what's going to go into the bottom of these things. So now the question is, what about my and mx? How are we going to find those moments? All right. Well, let's start with my. I think my might be a little bit easier. So let's see if we can build that up. So now remember what the moment is in general. We need to multiply mass times distance to the axis. Okay, so for moments, just let me remind you, it's mass times distance. I put here distance to the axis, so distance to the rotation point. So come back over here to this picture and you see this strip, this vertical strip. We need to figure out what its mass is, or for each of those little pieces, and then we need to multiply by their distance to the axis. So if we're talking about my, the distance to the axis is this right here. Okay, so that's how far that strip is from the axis. All right, well, that's just x, right? That's just the distance x. So then I need to know what the mass of that strip is. So how do I calculate the mass of that strip? If I've got a density per area, what do I do with that density to find the mass? It's the same thing we did down here. We multiply by its area, right? Well, its area is just the area of that little rectangular strip, which is this guy right here. So it turns out that to get my, we only have to alter this equation ever so slightly, because this is finding our mass. We now just need to multiply it by the distance away from our axis that we happen to be, which is an x. And the reason that we still have that integral from a to b is we're going to do that for every strip along the way. As we go from the left to the right, we want to do it for each one of those strips. So that's why we're integrating. So it's almost identical. The one and only difference is this guy right here. And we've got the x times, because that's how we get moments. Moments are mass times distance away. All right, cool. Not too bad. When we do an example, you'll see how to set this all up, and it's not that terrible. But this is just, that's how we're going to do it. There's the formula. Now, for the mx, this is a little bit more difficult. For the mx, now what we're talking about, instead of distance to the y-axis, we're talking about distance to the x-axis. And you can see why this might be a little bit more challenging with how we've got things set up, because now instead of vertical strips, I would want horizontal strips, because horizontal strips are all going to be the same distance away from the x-axis. But with the shape I drew, you can probably see the issue with that. Like, let's just go for something that's this distance away. And you think about that strip, it's actually going to be broken into pieces, depending upon what these functions are. And so if we really wanted to set these things up with integrals, we might need to have more than one integral for each of the different distances away. And depending on what f and g are, those may or may not be able to be determined. And right, so we want to actually approach this a different way. We want to keep using those vertical strips. All right, so the question is then, how do we do that? Well, we're going to be a little tricky here. And here's what we're going to do. So let me erase this black stuff, because we're not going to follow that. Instead, I'm going to think about this vertical strip. If that vertical strip, every piece of that has the same density, where would its center of mass be? Where would I need to balance that little strip? Where would I have to put my finger so that I balance it exactly? And it's what you think. Where would it have to be? What I'm going for is something like right in the middle. Right? If we're at the exact center of that strip, the middle of that strip, then it's going to be balanced. Here's that strip. I'm going to need to put my finger in the middle of it for it to balance, right? If I put it in the middle, it balances. If I put my finger at the end, it doesn't, right? So what we need to be is exactly in the middle of that strip. So here's the question then. Where's the middle of that? Well, do you guys remember how to find midpoints? If I just gave you two values on a number line, do you remember how to find the midpoint? So now this is where, since I can't see your pictures, I'm wondering if anybody's actually there. I'm just talking to myself.
And you just find the average of them, right?
Yeah, you just find the average of them. Okay, well, that means I need to find the average of these y values. Those y values are the f and the g. So I need their average. Well, we add those and divide by 2. So let's think about that midpoint. That's going to be f of x plus g of x over 2. And so that's, in essence, the distance away from this axis for that strip, if I were to bring all that strip into one point, into the balancing point. Okay, so it's this distance that I need to multiply to my mass. So the mx, it's going to be the integral from a to b, 1/2 f of x plus g of x times all the rest of this. Now, don't box that yet, because I'm going to make that a little bit nicer. And I'm going to rewrite them all up here just so that we've got them all together. So the mass is a to b rho times f minus g. The my, same thing, except with an x times it. And now the my, or sorry, the mx, if I make that a little bit nicer, it's going to be 1/2 rho of x times f of x squared minus g of x squared. Because these two are just a difference of squares. All right, so let's put a box around this, or a whatever. But those are the three things that we have to calculate if we're going to find a center of mass. So I'm just rewriting these real quick. All right, so I know this looks ugly. I know this looks terrible. And I know you're going, oh, this is going to be the worst thing ever. It actually isn't. Now that we've got these things derived, let me show you a couple of examples and you'll see how fast this actually is. How quickly we can do centers of mass. It's just a matter of doing 3 different integrals. All right, so while I'm erasing and getting ready for an example, let me know if there are any questions on my derivation, like how I got where I got. And oh, go ahead.
Oh, I was just wondering, since integrals give you negative and positive area, wouldn't where you want your x or your y axis to be where the integral equals 0? Or is that like an impossible thing to solve for?
Okay,
Does this make sense?
I totally understand what you're saying. And here's the deal, like, you're right, we're trying to get to 0 basically. But if we account for it this way, we do the way that we're doing it right now, what we're finding basically is the total moment, which gets averaged out when we divide by that mass. And so it kind of is bringing us to where we would have to move the axis so that it's balanced. And another issue that we ran into with the like negatives sometimes, like these might give us negatives. It's totally possible that it gives us negatives. But because we're doing that subtraction f minus g, we're always getting, if it's top minus bottom, we're always getting like actual area, which will be a positive amount. So that if we end up getting a negative, that's solely due to the distance away, either horizontally or vertically. So that I kind of gave two different answers to that, Tiana, because I wasn't sure exactly where you're going with the negative, but hopefully one of those was where you were going. Did I kind of address it?
Yeah, that answered it a little bit. I guess I was just thinking to get the XY axis to be exactly on your center of mass,
Mhm.
the areas would equal 0, right? Or the integral would equal 0.
Yeah, and how it ends up playing that once we find that center of mass, if we were to set it up, then with the distances, instead of being from the y-axis and the x-axis, if they were from the coordinate axes from that center of mass, that's the one that would end up being 0. So it's just
Okay.
it's this kind of weird deal where we're searching for the place that would give us 0, even though we don't get 0. And I know that doesn't sit well, but that's something that we do a lot actually in physics, because you can set coordinate systems however you want. And so when we run into something where we're not getting 0, like we're not going to get 0 for these usually, then that's telling us, oh, we need to be shifted by however much this gives. So that's kind of a common trick where you just go with, all right, I'm going to set axes somewhere. I'm going to use those and then adjust if necessary. So it is a weird thing, but it's a process we do all the time. All right, we ready to see an example? See if we can knock one of these guys out. All right, so here's what we're going to do. Let's find the center of mass. Let's erase this real quick. Let's find the center of mass of the region bounded by and I'm going to give you a couple of curves here. One of them is going to be 4 minus x squared. And the other one is going to be x plus 2. And I'm going to go with constant density. Okay, so we're going to find the center of mass for this region, and we're just going to assume that it's got constant density. That'll make it so that the integrals are a little bit easier. So real quick, before I go too much further, when you have constant density, the center of mass sometimes goes by a different name. This is sometimes called the centroid. So centroid, that's the center of mass of an object with constant density. So if you ever see that centroid, just realize that it's center of mass. Just so you know some naming schemes in math, anytime you hear oid, that means shape. Spheroid, it's a shape that's in, that's in the shape of a sphere. Ellipsoid, hyperboloid, right? So a centroid, it's the center of the shape. All right, well, anyway, so let's see if we can figure this out. Now, first thing I'm going to do is I'm going to draw the picture so we can get an idea of what we're looking at. And then I'm just going to dive into the formulas and do our thing. All right, so y equals 4 minus x squared. Sad parabola. Frowny face. Its vertex is up at 4. So it does something like this. All right, so there's our 4 minus x squared. Y equals x plus 2. That is a line. Goes through 0, 2 as a y-intercept, has a slope of 1. So it does something like that. So I'm looking at the region that's bounded by those two. So that's this shape right here. All right, let me actually make that look like a line instead of something that's been bent. That's a little bit better. All right, so there's our shape. So we want to find its center of mass. Okay, so let's calculate these three things. Let's calculate the mass and the two moments, and then we'll get our centers of mass. All right, so what's F and what's G?
F is the parabola and G is the line.
Correct. So we've got our parabola is the top, the line is the bottom. So here's our mass then. We start with mass. Mass is going to equal the area from A to B. We'll worry about that in a second. But we're going to have a constant density rho. So I'm just going to leave it as rho times F minus G. So 4 minus x squared minus x plus 2. We're going to be able to pull that rho out. And then if I just distribute in group like terms and all that lovely stuff, I get 2 minus x squared. So that's going to be a pretty easy thing to integrate. But of course, we still need to get bounds on that. Uh-oh. Where are the bounds? Or how are we going to figure out those bounds?
Set the two equations equal.
There you go. Find the intersection points just like always. Thanks, Deanna. Yeah, we're going to set those things equal to each other and solve. So we'll have 4 minus x squared equals x plus 2. That's x squared plus x minus 2 equals 0. And a little bit of work on that will get us from minus 2 to 1. So this will be from negative 2 to 1. So I can go ahead and do the integral on that. We get rho times 2x minus x squared over 2 minus x cubed over 3 that we're evaluating at minus 2 and 1. And I'll just tell you that that ends up giving us 9/2 rho. So you plug those numbers in, you're going to get 9/2. Okay, so the mass of that plate is going to be 9/2 the density. So if you tell me what the density per area is, I multiply that by 4.5, and that's the total mass. Okay, cool. So we know what we're going to divide by for both. All right, well, let's go ahead and find our my next. So for my, here's how this is going to look for this specific problem. Again, it's going to be an integral from -2 to 1. We're going to have rho times x times the difference in those two functions, which again was 2 minus x squared. Okay, so we're just using the fact that it's rho times, or x times that stuff. So this is rho times the integral from -2 to 1 of 2x minus x squared minus x cubed, which again, just power rule. So now we're going x squared minus x cubed over 3 minus x to the 4th over 4. All right. So the question then is, what do we get when we do that? And we get -9/4 times rho. So another pretty easy one to calculate. Just a matter of plugging those numbers in. So you get -9/4 and then it's times rho. So there's our my. All right, so lastly, we have to get mx. Now mx is going to look a little different. It's still going to be integral from -2 to 1. And we still have our rho, but this time it's a difference, or I mean, there's a 1/2, and then the difference of those functions squared. Right? So there's the 1/2 rho times, and in this case, it's going to be 4 minus x squared squared minus x plus 2 squared. So if you go back and you look at what I wrote for our mx, we had this. Okay? So it's going to be 1/2 rho times the difference of those things squared. So I'm going to pull out the 1/2 rho. And then I have to do a bit of algebra on this. So I'm going to FOIL, I'm going to group like terms and all that. So I'm going to get x to the 4th. That comes from this x squared squared. The next thing I'm going to get in terms of the polynomial decreasing are going to be x squareds. And I'm going to get -9x squareds. 8 of them come from this, and then 1 of them comes from the x plus 2 squared. Then I'm going to get some x's, and I'm going to get -4 of them. Those all come from right there. And then in terms of the constants, I'm going to get 16 minus 4, which is 12. So there's our polynomial that we integrate here. So that's going to give us 1/2 rho times x to the 5th over 5 minus 3x cubed minus 2x squared plus 12x. Again, we're going to plug in our -2 and our +1. And what that should give us is 54/5 once everything is done here. Rho. No, that's not right. Hold on. I gotta figure this out. Give me 1 second. Now it should be 24/45, which is 8/15. I think. I'm not terribly confident in that number. I didn't write it down. But regardless, we get whatever that value is. All right, so let's finish this off. Let's get our center of mass. So x bar, that's my over the mass. So my was minus 9/4 rho. And we're going to divide that by 9/2 rho. So the first thing I want you to notice that the rows cancel out. It didn't actually matter what the density was. And that's kind of the nice thing. When you have constant density, you can ignore it when you're finding center of mass, but only if it's constant density. Okay, so minus 9/4 divided by 9/2. You do a little bit of magic on that and you get negative 1/2. All right, so then we go to y bar, same deal, but it's going to be the x, the mx over the m. So our mass is again 9/2 rho. And then we're going to take our mx and divide that. All right, well, that's going to be our 8/15 rho. And again, the rows cancel. All right, so we do this division. I screwed something up. I don't know where I did it, so I'm just going to go with what we got, which is 16/135. I think I gave you the wrong value here. I definitely gave you the wrong value there. I think it's, I apologize. I'm trying to, I should have calculated this number. Maybe it's 54/5. I don't know, something funky's here. So if you get a different value, just go with it. It's because I messed it up. But regardless, let's just take a look at what this is saying then. The center of mass, the x bar is negative 1/2. So that means that the center of mass is somewhere over here, negative 1/2. And then our y bar is 16/135. It's actually supposed to be 12/5, but anyway, it's somewhere up in here. And so this is the location of our center of mass. That's where the pivoting on either side is the same. So it really comes down to just having those three things to calculate: the mass and the two moments. And then you just divide those suckers and you can get your center of mass. All right, so this is another big application of integrals because we're adding up lots of little things. It's just in this case, the little things are our moments and we're using them to balance. Now, centers of mass you're going to see again later as you progress through calculus, because we start learning other techniques to deal with densities that aren't just like, you notice that these densities I told you, in this problem they were constant, but in what we derived, they were densities that only depended on x. Well, if you've got densities that also depend on y, you need to use what we call double integrals, which you'll learn about later. So as you progress through calculus, you will see centers of mass again when we want to deal with more complicated density distributions. And I know I just said more complicated, and you're probably going, oh my God, I don't know if I can do one of these problems. Yeah, they get more complicated. And you'll see that these aren't really that bad once you get a hang of them. Anyway. It looks like I ran a little over time today. I apologize, but I wanted to make sure we got through this example. Just a couple things for next week. The plan is for Monday. I'm anticipating that I will be back on campus. So we are going to plan on that. However, there might be a last minute change of plans. I will let you know as soon as I possibly can. Here's the deal. I have to get a negative COVID test before I can come back to campus. I'm going to take one at 7 in the morning on Monday. Got it scheduled for 7 in the morning. So I will find out by like 7:30 if I'm coming or not. Right. So there could be a very late minute, nope, we're not going to be on campus. So watch for a message. Should be there for sure by 8 in the morning. Watch for that to come through Canvas. So if for any reason I'm still positive and I'm not allowed on campus, we'll still be in here on Monday morning, but that's not the plan. The plan is to be on campus. Okay, so I'm sorry that it's going to be such a late last minute notice, but there's nothing really I can do about that. And then the other thing is I'm going to, instead of having the quiz today, let's move that to Wednesday. So just so you know, and I'll send out a message that lets everybody know about this as well. But my plan is to have the quiz on Wednesday to kind of make up for this one, because we didn't have one scheduled for next week. So let's do a quiz Wednesday. And it's going to be on the sections that are, I don't remember the numbers, so I'm just going to tell you the topics. So it's the volumes using shells, and then the arc length and surface area. So whatever section numbers those are, which I know you guys can figure out, but it's those two sections, okay? So the volumes using cylindrical shells and arc length and surface area. So we'll do that on Wednesday, and again, should be in class. All right, so I think that's got everything I've got. Any other last minute questions before I stop the recording here?
Yeah, when do you think you're gonna post the exam scores?
Oh, I keep forgetting to do that. Thank you for reminding me, Edward. That will happen today at some point. I have a meeting right after this on Zoom, so it'll be a while, but I'll make sure I get to that today. Thank you for reminding me. I just keep forgetting to do it.
Thanks.
All right, anything else? No? Okay, well then with that, have an excellent weekend. Hope everybody stays safe and healthy, and I will see you all on Monday, hopefully on campus. All right, have a great weekend, guys.
Thank you. Bye.